Okay, today is November 22nd, 2011. We're working on lesson 5.6. So lesson 5.6 is a recap of all the lessons we've done before. So it's almost like a review. We're going to be focusing on linear models as well as quadratic equations and exponential equations. So what we're going to be doing is we're going to be getting sets of data, and we have to choose which model, and they usually call them regression models, which regression model fits the data best. Okay? We may find out that none of them do, or we may find out that one's not perfect, but it's very, very close. It's almost like a line of best fit using our data. Instead of graphing the data, though, because sometimes it can be very hard to tell the difference between a quadratic and an exponential, depending on the curve, we're going to use what we used the other day. We're going to use our first differences, second differences, and then our division to find out growth in decay. So I have a chart here, and it's time versus voltage. Now, luckily for you guys, this has already been set up, and I've put it into X and Y. But it's very important we remember that our independent variable goes on the X-axis, and our dependent goes on the Y. So as time passes, the voltage of this electrical appliance decreases. Makes sense, it starts getting old. So we want to figure out if the relationship is linear, quadratic, or exponential. What is the first thing I do if I want to figure out if it's linear? What's it called? First differences. So we're going to find the first differences of our dependent variables. So I'm going to take the number on top. 9 subtract 7 gives us 2. 7 subtract 5.2. Is that 1.8? 5.2 subtract 3.9. It's going to give us 1.3. 3.9 subtract 3 gives us 0.9. And 3 subtract 2.3 gives us 0.7. If you look at this, our first differences, it constantly decreases, and they're not nearly close enough to being the same number. So we know this is not a linear regression. We know this is not linear. Our first differences are not the same. In order to set up our second differences, we'll be subtracting our first differences from each other. So we set up our chart again. Get used to setting up this chart. It'll help you organize everything we're doing. Second differences. If second differences are the same, what is that going to tell us about our model? It's quadratic. Good. So, second differences. I take the first differences and subtract them. So I take 2, subtract 1.8, I get 0.2. 1.8 subtract 1.3. 0.5. I get 1.3 subtract 0.9. I get 0.4. And then 0.9 subtract 0.7, 0.2. Again, if we look at our numbers, 0.2, 0.5, 0.4, 0.2, really no rhyme or reason to them. They aren't close enough to be considered the same numbers. So, is this a quadratic relationship? No. Second differences aren't the same. Can't be quadratic either. So finally, the last type of regression we're going to use here is exponential. And in order to find exponential, we're going to be dividing our terms by each other. So first off, let's take a look at this before I decide to name this. Our voltage, is it increasing or decreasing with time? Decreasing. So am I working with growth or decay if it is to be one of these? Decay. So that's important. So we're going to look at our decay factors. Make sure we know the difference. Because it's going down, that means this model, if it is exponential, is a decay model. Decay factors. In order to find decay factors, we're going to divide our y variables, or our dependent variable. So we have 9 divided by, you know what, I'm going to do it the other way, just because the other day we were doing the top number from the bottom. This time we're going to do the bottom number from the top. We'll still get the same type of ratio as long as we keep which bottom and top in order. So if I decide to divide the bottom number by the one above it, I have to keep that pattern. If I decide to divide the top number by the one below it, I have to keep that pattern. If I start switching, my ratios will change. We won't get the right answer. So our very first one is 7 divided by 9. And we get 0.7 repeated. Okay, so we get roughly 0.7, maybe 8, we'll round it to. The next one, I divided 9 by 7. So now again, I'm going to do the bottom number by the one above it, 5.2 by 7. 5.2 divided by 7, 0.74. Next one, we'll do 3.9 divided by 5.2. 0.9 divided by 5.2, 0.75. And finally, oh no, there's 2 more. 3 divided by 3.9. 0.76. And finally, 2.3 by 3. .76 again. Now, in our decay factors, are the numbers exactly even? Do they work out perfectly? No. But are they relatively close in terms of their decimal place? If we were to round to the 10th column, everything would roughly be 0.7. 1 or 2 of them might round up, but roughly all of them are 0.7 in terms of our decay factor. Now, the only thing that was close to that was our second differences. But even in our second differences, the 10th column of the decimals, they were all changing. So in terms of a best fit, our decay factors are all roughly almost the same number. Our decay factors work. This is probably an exponential model. Now, this is what's important with data. Data is being collected in a survey, so it won't always fall perfectly on a line. But if we're looking for the best fit, we need to try all 3 and figure out which one works best. It is possible that none of them are even close, and we couldn't possibly call it any of them. But in this case, our decay factors have very close numbers. They're off by 1/100th of a unit. So they're relatively close. So we're going to say that this is exponential decay, this model. And what we'll do is we'll try to plot a little of it. Okay, so we have our graph. What I'm going to actually graph is the actual data. So I'm not graphing the first differences, second differences, or our decay factors. We're graphing the actual data, and I'll write it down as we're doing it. This is our time. So we're going to write down our coordinates along with it. So we had time and voltage. We had it on a chart on the other page, right here. I'm just going to write the coordinates down on our second page here. So our very first coordinate for time and voltage was 0 and 9. Okay. So 0 and 9, that means time was on our x-axis, it was our independent, and voltage was our dependent variable, which was our y. So 0 and 9, this is our first model. Our next number was 2 and 7. 2 and 7. Next one was 4 and 5.2. 0.2. 6 and 3.9. 8 and 3. And then 10 and 2.3. 2.3 over here. So if we take a look at this, it's actually a line that's starting to curve and get flatter and flatter. Now, from my first look, the can be pretty hard to tell what this is. It might be a very large quadratic, a very large exponential function. It, to the eye, almost looks like it could be straight. So by just graphing these, I wasn't really, or I personally wouldn't be able to choose a regression model that would fit perfectly. That's why on our other page, we took the data, we found the first, second differences, and decay factors. And that was the best way to go about finding which regression model worked best. So just by graphing, it can sometimes be very difficult by our eye to tell which model works best. So we have to make sure we remember all three of these rules: first, second differences, and decay factors.